Hi everyone, and welcome to our video where we will be sketching a rational function. Now, we're in a calculus class, so we'll be doing derivatives and second derivatives to make this graph as accurate as possible. We can use technology though, because usually we can. Now, if we cannot use technology, then all these steps would make it to where we can get it as accurate as possible. But first, I am just going to graph it on a graphing calculator just to see it right away. And then we'll go through what is important for what they would want in the calculus steps. Okay, so I'm just going to type this in exactly as I see it. So x minus 3 divided by x squared plus 2x squared plus 2x minus 15. Okay, so we get this. So we get this here. So that's our sketch of this graph. Right, very quickly, right? The calculator does it instantly. We'll make it to where it's a little bolder. Okay, however, we do have some information that we can get from this that we're going to need to copy down in our calculus part. Okay, so for instance, there are asymptotes, and we can see one at x equals -5. So there's one right there, and then we can see a horizontal one as well. Okay, so y equals 0 is another asymptote. So that's where the graph goes to. So if you zoom out far enough, we can only see the blue and green because that's where the graph's headed toward. Now, the red graph zoomed in, we see is curvy. Okay, so we do want those curves involved. Okay, and let's continue to break it down. And even from here, we can start to get like points. Okay, so you just click and see everything that's important. All right, anyway, let's get to the calculus part. So we have pretty much the answer. We can graph it with the calculator. But let's break down this process of what they might want. So in these problems, if you can factor, usually it's a good idea to factor. So for instance, this becomes x minus 3 over x. Looks like it's plus 5 times x minus 3. Okay, so we factored it, and notice that the x minus 3's are the same. They would cancel, so we have this function instead. However, we do have a special rule with this. These only cancel in this part when x is anything but 3. Okay, the reason for that is because when x is 3, you notice, right, if we plug the x equals 3 in right here where I'm bolding, that would put a 0 down in the denominator. And we know division by 0 is undefined. Okay, so what we currently have in this place is we do have a whole at x equals 3. Okay, so that's equals at x equals 3. And then we also look at this part here, where I'm also now bolding. If I were to plug in -5, what we would have instead is a vertical asymptote. So vertical asymptote, oops, let's spell it right. That's okay. Asymptote at x equals -5. Okay, so these both come from the restrictions in the denominator. Okay, so the whole comes from when the denominator is 0 but has a common factor. But with a common factor in the numerator. Whereas the vertical asymptote occurs when the denominator is 0 with no common factor in the numerator. Okay, so when denominator is 0 and no common factor in numerator. Okay, and these rules go back to pre-calculus type of stuff. Again, I'm going to go back and forth between the graph and what we'll do. Notice we already had the x equals -5. We saw that earlier. So we have the vertical asymptote. Notice this graph, though, does not show the whole. Okay, so it said at x equals 3, there should be a whole. So I'm just trying to click on it. Let's see it. We can make the decimal. There we go. So we have a whole there. Okay, so what we really want though is the actual point. So I do want to know that y coordinate. So yes, it's undefined in the function, but we can do a limit. You see that? Because the left and right go to the same thing. So we can do a limit to figure out what that point is. Okay, so let's do that. So a lot of information just from this vertical asymptote. So for the whole, one last thing about the whole. Let's do the limit as x goes to that 3 of the function. But let's just use the simplified fraction. So still the limit as x goes to 3, but of the 1 over x plus 5. So this is what we would have done from limits back earlier in this class. So remember, we would cancel the common factors and then apply the limit. So now we would have 1 over 3 plus 5, which is 1/8. So that means our whole is the point 3 comma 1/8. All right, so now I've got some information. I'm going to box that. That's important for us. We also had the vertical asymptote. I'm going to just rewrite it down next to it. Vertical asymptote is x equals -5. Okay, and actually let's do that in red. Oh, I said red and I didn't do it. There we go. I'm going to box that in red so I can start to graph these things. Okay, so the vertical asymptote at x equals -5. 1, 2, 3, 4, 5. And then now we usually do a dashed line to show it on our pictures. So there's the vertical asymptote, x equals -5. And then our whole, let's do that in this blue color, 3 and 1/8. Okay, so 1, 2, 3 and 1/8 right there. So that's an open dot. Okay, so it's a little tough to see, but that's an open circle. So that's what we'll do also, just to show it on this one as well. Let's type in that 3 and 1/8. There's that point, and let's change it into the whole. There we are. Okay, and even on these, how about we change these to dash lines? Okay, so there's all of our graph. And I'll even change these colors to match what I was doing so far. All right. This one was blue. Okay, anyway, so there it is, just starting to match, again, what we had from our information with already what we know. But the whole we didn't know, or maybe we wouldn't have known right away. So we did find it though. Okay, so that's all the denominator stuff. And all of this, these are just different steps that we can do. It really doesn't matter too much the order. So when I have step 1 here, identify the domain or the interval of interest. I know it's a rational function. I know the domain has restrictions in the denominator when the denominator is 0. So that's why I went to that first right away. So I got those 2 pieces right away. And then now let's find some other information. Well, because it's a rational function, so it depends on the function we have based on what we'll be doing to these things. But because it's a rational function, so this first part we did because it was rational. So just because there's something in a denominator. Same deal with this number 2. Again, because it's rational, what I want to know is I want to do a limit. So I want to know the end behavior. And you could do that end behavior actually on non-rationals as well. So I'm just going to actually scribble that out. Let's just do the end behavior and say it is doing the limit as x goes to plus or minus infinity. And we can merge the 2 together, so plus and minus. You might need to do them separate on some problems, but on this one it won't matter. Okay, so the way that we do that, so the limit as it goes to infinity. Here's our function again from the start. But remember, when it goes to an infinity, plus or minus, it doesn't matter which one. All we have to do is take the leading term of both the numerator and the denominator and divide and see what that looks like. And we get here still. So I just took the leading terms only. So I only care about those. And then now I'm going to do the limit. Well, x over x squared reduces. It's 1 over x. Remember, if you have 1 over x or 1 over x squared or 1 over x to the 5th, so if it's a constant over an x, then this becomes just 0. Okay, so that means our end behavior is based on this limit, which gives us the horizontal asymptote, horizontal asymptote y equals 0. So remember, limits are giving you something that is like a y value. On this problem, it's a y equals 0 line, the whole horizontal asymptote. So that's what we'll put in dashed green right here. Okay, so there's our horizontal asymptote. Let's box that like that. Okay. All right, so rational function, we looked at the restrictions, we looked at the denominator, and then I moved on to end behavior. So it didn't matter if it's a rational function or not, that's why I scribbled it out. End behavior is doing the limit as it goes to an infinity. All right, now let's get to the zeros. Okay, so the zeros, that's where the whole function is set equal to 0. Okay, so I'm going to say here's number 3, the zeros. That's where f of x, the whole thing, equals 0. Well, our whole function, our original function was x minus 3 over x squared plus 2x minus 15. That's what we set to 0. And then, well, we can instantly put a 1 under that 0. And then we can cross multiply. So this denominator we can multiply out, because we already have information on the denominator. That was our first step. So that's why we can cross multiply it to make it go away right away. And then we have x minus 3 equals 0. And it looks like x equals 3 would be the answer to this. However, okay, so again, tricky in this problem because we had a hole at x equals 3. So back to this. So we had a hole at x equals 3. That means it's not a 0. Okay, so that was part of a restriction. Okay, so x equals 3 was already labeled as a restriction. So if that happens, then that means this actually is not a 0. So remember, zeros are x-intercepts. So I'm going to erase this. So we would have plotted it right there if it was really a 0 right on the x-axis, but it's not a 0. So that means, because we already have a hole there, so that means we should get rid of it, or not even consider it. Okay, so again, interesting things that can happen with rational functions. And I'd say use your calculator to always double check. I mean, we can also see there is no x-intercept on our graph. So if there was, it would have touched the x-axis. Okay, so we know that again from technology. Okay, anyway, so with the zeros, that was it. Then one other thing that we can get, I'm going to say this is number 4. Let's get the y-intercept. The y-intercept is when we let x equal 0 in the function. Okay, so we would do f of 0. Again, I'm just kind of eyeballing this function again over and over again. When we plug in 0, we would have, and we could do it in the simplified one. So that one's easier to work with. Let's use that. So if I plug 0 into that x, I would have 1 over 0 plus 5, which is 1/5. So we get the y-intercept is 0 and 1/5. Okay, so 0 and 1/5. Okay, so let's see. Is that a match on this? Yeah, 0 and 1/5. So 0 and 0.2 is the same thing as 0 and 1/5. Okay, so there's the y-intercept. I'm just marking it with my point 0 and 0.2 against the same thing. Okay, so we got our y-intercept there too. Okay, so we're just ticking away. Okay, so these so it's a lot of pre-calculus stuff. So we haven't really done too much calculus except for these limits. And then now let's get the derivative stuff going. Okay, so the derivatives will tell us if there's any local maximums, and the second derivative will tell us how its concavity is. Okay, so let's, running low on room already. Okay, so number 5, again, let's use our simplified one. So 1 over x plus 5, because it is the same thing. We just know that something weird's going on at 3, which we already have accounted for. Okay, so at x equals 3, we've got something weird happening. But this is easier to do our derivative with. Okay, and there's different ways you could do it based on how it currently is right now. Okay, and let's label number 5. Number 5, we're going to do a derivative. Let's say first derivative. And you could do the quotient rule with it. However, what I'm going to do, I'm going to rewrite it using a negative power like that. So that way I can do the chain rule with it. So the chain rule tells me I can move the negative 1 to the front and then still have x plus 5. Minus 1 from the power would be negative 2. And then times by the derivative of the inside, the x plus 5 derivative. Well, the derivative of x plus 5 is 1. And so this simplifies real nicely. That is our first derivative. And we can rewrite it as needed, but I'm gonna rewrite it in two separate ways. So I don't need to show the times 1. So I'm gonna write it like that, and then let's also write it like that. Okay, so it's just the C in bold. Okay, so there's our first derivative, and then the first derivative, the usefulness of it is when we find critical values. Okay, so the critical values are where the f prime of x is equal to 0. So we would set 0 equal to negative 1 over x plus 5 squared. And here I'm just going to eyeball it and say, well, at x equals negative 5 is where we have a problem with this. Notice there is no x value that actually makes this 0. Okay, so we can say no zeros, none, but this function is undefined at x equals negative 5. Okay, so that's important for us. We already knew that. But what it does is it lets us make our number line. So there's our x values, f prime and f, and it will let us know if we have any local maximums or minimums. Okay, so I remember we would plug in anything bigger than 5, negative 5 I mean. So like if I plug 0 in to my f prime function, so here's my f prime function that I'm starring. If I plug 0 into that, we would have gotten f prime of 0 is negative 1 over 5 squared, and that's a negative value, so negative 1 over 25. Okay, so that means that's negative, which means f should decrease. Okay, and then let's plug in something smaller than negative 5, so like x equals negative 10. So f prime of negative 10, kind of messed that up. So if we do f prime of negative 10 and we plug that in, it would have been negative 1 over, so again, I'm using this starred one. Negative 10 plus 5 is negative 5, but that squared is still 25 down below, still negative 1 up top, so still negative. So still decreasing. So it's decreasing the whole time. There is no local max or min. All right, so that's good to know. So we know it's decreasing the whole time. Now the last thing, let's get our second derivative. Let's do that in blue over here. So the second derivative, again, using my f prime, which is already starred, I'm starting it again. Using this one, I'm going to do the chain rule again. So we have f double prime of x would be positive 2, and then x plus 5 to the negative 3. Okay, so we get that. And then, excuse me, and then just like with the first derivative, we'll do our critical values. So we'll set the second derivative equal to 0. Note again, I can rewrite that as 2 over x plus 5 cubed. Well, the same thing happens that happened in the first one, is that there's only one bad x value, and it's at negative 5 again. So that's what we'll use on our number line, where we have our f double prime and f, and there's our x value. Now the second derivative, remember our friends. So the signs of the second derivative tell us how the concavity is of f. And so when we plug in something smaller than negative 5, let's start over here, like negative 10 again, into our second derivative. Well, when we plug that in, we would get 2 over negative 5 cubed. That would be 2 over negative 125. So that is a negative value. So our second derivative is negative, which means that it is concave down like a frown. And then when we plug in something bigger than negative 5, like 0, we would get 2 over 5 cubed, which would be 2 over 125, which is positive. So that means it's concave up like a cup. Okay, so now we know the concavity of everything. So now we can complete the whole sketch. So we have the concavity, we have how it decreases, or it decreases only. All right, so left to right. And again, we already knew it. Here it is. So notice it's decreasing the whole time, drawing downward from left to right. Notice this concavity is concave down like a frown. Okay, so it matches, again, what we found. And then we're just drawing it the best we can. Now, it might help to plot actual points. For instance, like it might be good to know what x value of negative 6 is, and maybe let's do negative 4. Now I'm going to use the graphing calculator to see that. Okay, so I just want to see what I get for negative 6. So negative 6 and negative 1, and then negative 4 and 1. Okay, so that's nice. So negative 6 and negative 1, negative 4 and positive 1. That way we have a little bit of accuracy to it. A little bit more. And then now let's sketch in the rest of the graph. So we know it's decreasing the whole time, so that means I'm drawing downward the whole time. And there we go. And this is concave down like a frown. And now, again, I'm drawing it downward the whole time. And then this is concave up like a cup. And then it hits the hole, and then it keeps going. Okay, like that. Okay, so there it all is. And again, we already knew all that. Notice when we zoom in, we can see more of a curve. Again, when we zoom out, so this is probably what our graph looks like. So not much to really see when zoomed out too far. Usually we like to exaggerate the curviness of it like we do when we zoom in. Okay, but now that's about it. If we wanted to sketch, there's our sketch that is accurate as possible. Again, we could have gotten this without the calculator. That's what we did. So we took a long time to do all that. Hopefully you stayed patient with me here. Now, if it did ask where is it increasing, decreasing, and where is it concave up and concave down and all that information, well, we do have it. It is decreasing the whole time, but it is decreasing with some breaks in between. So I'm just going to put it right here because I'm pretty much out of room everywhere else. So the graph decreases from negative infinity to negative 5. And then negative 5, here's where you have to be careful. There was a hole there. We just have to keep remembering that. So there is a little break. So negative 5 to 3, and then 3 to infinity. So if it does ask for that type of stuff, we still do have it. And then it does concave up and concave down. So concave up, that was from negative 5 to really infinity, but again, the hole there puts a little pause on it, so make sure to account for the hole. So there's that one, and then concave down, negative infinity to negative 5. So there's the calculus type of stuff that they might ask for, which we have from our number line. Now there were no inflection points, there were no relative maximums, no or minimum, so no relative extremas, and then no inflection point. So that's other stuff they might ask for, but on our problem, we didn't have any. And that happens pretty frequently with these weirder functions. Okay, but that is it. So one super long problem. Graphing again. So if you just said, I'm just going to graph it, that if you could use a graphing calculator, yeah, that probably gets the job done. Now, you might miss some information like the hole, but that's where the factoring would help, and try to remember that type of stuff. Okay, otherwise, the first derivative we got, second derivative we got, so we did all that. If you do have any questions, please let me know. Otherwise, thanks for watching.